Okay, so shall we start?
Okay, I will start with a brief introduction.
Okay, thank you.
Jiaoyan. So Dr. Jiaoyan Li is the lead organizer of the CFSM seminar series. So she is currently an assistant professor at the State University of New York at Buffalo. So before joining the UB, she was a research associate at the DOE Idaho National Lab during 2018 to 2020. And she was the hybrid engineering fellow in the School of Engineering at Brown University during 2015 to 2018. So she obtained her PhD degree in mechanical and aerospace engineering from George Washington University in 2015. She her research interest is multi-scale modeling from atom to continuum mechanics and the computational mechanics and high performance computing. And usually the application is targeted to the nano, bio, and energy systems. So Jiaoyan, please start your seminar.
Yeah, thank you, Zen, for the kind of introduction. And hello, everyone. It is my great pleasure to share my research project on the topological toughening of 2D materials. So in fact, this topic was done like back to several years ago when I was at Brown, and because of the job change, I kind of leave the academic area for several years. So I couldn't continue this topic, but hopefully I can take this opportunity to get back to the fracture mechanics, my main like a solid material like area. So with that, I think today I will mainly talk about 5 parts. So I will first present my motivation for this work and explain why we want to toughen the 2D materials. And then I will show a structure illustrating how the nature can toughen the thin membrane. So the phase field crystal model is adopted here for the numerical simulation. And as an example, so I will go into detail ways to explain about the design of the nano bubble graphene. And in fact, from the background picture, you can see you may want to have some first impression about the nanobubble graphene. So basically, you can see the out of plane like a geometrical like a bubble with different size and the shapes integrated with the flat graphene. And I will show you how we do this kind of design. Using the phase field crystal model. And also, and then at the end of this talk, I would like to point out some kind of potential future opportunity, and hopefully I can also pick up from there. So of 2D material like a graphene and silicon like hexagonal boron nitride and molybdenum disulfide. So most of the 2D materials, so they have a lot of attentions because of the superior like properties. So they are very, very thin and with only a single atomic layer thickness. They are light but strong and hard, and they have like various kind of like electronic properties and cover from conductor, semiconductor, and the insulator. So they are also transparent, bendable, stretchable, and they have been widely used in many applications. So for example, the graphene has been used as a flexible electrode in the touch screen due to the high like carrier mobility and density. And in this work, so we are trying to fully utilize this thin feature, in fact. So this feature reserves a lot of valuable flexibilities for the 3D out-of-plane structure design. And so although the 2D material have many superior like properties, the bad news is that they are very, very fragile. So an in situ fracture test has confirmed that the fracture toughness of graphene is only about like 16 joule per meter square. And the hexagonal boron nitride is a little bit higher than graphene, but not so much. So the molybdenum disulfide, as you can see from this picture, is a AFM like in situ initial fracture test of the MOS2. And so although they do not report, the author do not report the fracture toughness, but we can see the clear cleavage like a surface. And this cleavage surface implies a brittle fracture behavior. So then we want to understand why graphene and its analogous are so fragile. So we basically the common understanding is that metals and alloys are usually very, very tough, as you can see from the picture on the right. So when cracks in metal and alloy encounter the external loading, so the dislocations in fact can emit from the crack tip and form the plastic zone, so which greatly increase the fracture toughness, and not to mention the complex interaction between the dislocation, green boundary, and the green boundary and or the twin boundary, so as we can see from this picture. So on the other hand, from this simple fracture test of graphene using molecular dynamics, we can see that the initial crack propagates when the critical loading is achieved without forming any plastic region or emitting any dislocation. And the color here, in fact, represent the real stress along the loading direction. So people were also wondering if the fracture toughness of polycrystalline system could be higher than the pristine case. So the answer, in fact, is yes. Polycrystalline system has intrinsic dislocations as green boundary. So therefore, during the crack propagation, the intrinsic dislocation can alter the crack path a little bit, as you can see from here. So the crack can propagate along the certain direction of the green boundary. So with the contribution from the green boundary, the calculated fracture toughness is around 20 joule per meter square, higher than the pristine case, but still it's not very good for the engineering application. I mean, we still consider this polycrystalline graphene as brittle material. So although we notice that green boundary formed so we also notice this green boundary formed by a string of dislocation. So this green boundaries, so during the crack propagation, in fact, we don't see any newly generated dislocation, new pair of dislocation or new green boundary. And with that, we can say that dislocation in 2D material is neither regenerative or mobile. And that is the main reason why the 2D materials are so fragile. It's mainly because of the lack of energy dissipation mechanism intrinsically, and therefore the material is very, very brittle. And based on the study for the polycrystalline system, we have known that the green boundary can contribute to the fracture enhancement, but not so much. But we still want to explore how we can take more advantage from the green boundary. So let's first take a look at the green boundary in graphene. So from the TEM image, the green boundary in graphene, in fact, is a pile up of the pentagon and the heptagon dislocations. So also there is a direct correlation between the defects and the surface winkling. So basically the green boundary or the dislocation or the defects inside of the material, the 2D material, can result in out of plane deformation. So this can serve as the basic foundation for our topological design and the green boundary. So green boundary and the dislocation can be used to compensate the curvature variation for the out of plane like a structural feature. And so for this project, one of the main objectives is to answer how to toughen 2D materials, and to be specific, how to introduce effective toughening mechanisms into the 2D system and utilize its geometrical feature to enhance the fracture toughness. So let's first try to get some inspiration from nature. So during the lifetime of a flying insect, for example, this kind of dragonfly, So the wing of the dragonfly is considered as a very thin membrane, and the wing, in fact, is subjected to mechanical like forces and the deformation for millions of cycles during the lifetime of the dragonfly. So sometimes the defects in this membrane also in the wing also happen, and these defects can also reduce the insects like flying performance and skeleton biomechanical functions. So as we know that, so we know that this dragonfly has the system to do self-healing, but in fact the microstructure of the flying insect also contribute a lot to resist the damage evolution. And the figures on the top, we can see the microstructure of the wing of the dragonfly's wing. So we can see this kind of cross wings and also the longitudinal wings. And so we also see this kind of more like a wavy, like a pattern inside of each like cross wings or longitudinal wings. So biomechanics researchers have done this kind of stress, have measured the stress strain curve, which is shown here at the bottom. So we can see that during the crack propagation, the wings can take some loading while the crack tip is trapped by the first cross wing, and the second one and the third one like one by one. So it kind of deflect the main like crack propagation direction towards the longitudinal wing until the like final failure. And this finding directly demonstrate how the microstructure can contribute to the biomechanical like behavior. So we also get some inspiration from here. So what we do here is to just choose kind of similar like a wavy pattern, the standard solder like a wavy graphene ribbon, and we also try to fuse this kind of wavy pattern with the flat pattern together. So we could construct the building block for the wing pattern graphene, and then we can just repeat this unicell along the like two direction, like a horizontal direction and the vertical direction, so that the larger samples can be assembled as shown as this as in this picture. So the color here represent the out of plane like atomic position. So where the red color give us the highest position and the blue color give us the lowest position. So we can see the alternative like arrangement of the high part, the crest and the valleys in the wavy region. And here we can consider the wavy region, the wavy ribbon as the soft face of the structure, and the flat ribbon as the hard face of the structure. Then the interlacing of the soft and hard faces present a typical structure with enhanced fracture toughness. And when the crack tip falls into the hard face, then it can propagate like more easily. But when the crack tip falls into the soft face, then it might be just trapped over there. So here, we would like to emphasize that the pentagon and the heptagon dislocation, the dislocations will appear in the transition area, as you can see from here. So that dislocations can help to compensate the change from the flat surface to the wavy surface. And also, we do the fracture test for a sample with the edge crack. And as you can see from the bottom pictures, so during the fracture test for this sample, so the crack tip first become blunting when it meets the first wavy part. So again, so the wavy part is considered as the soft face of the structure or the system. So it can kind of trap the crack tip for a while. But if we further increase the external loading, so we can see some generation of the ductal cracks. And so this ductal crack, the generation of the ductal cracks, in fact, are related to the defects in the dislocation in the transition area. And then finally, if we increase the strain up to like 9%, then we see a lot of we see more like a Dr. crack, and we also see the crack path deviation. I mean, the crack path deviate from its main direction as the of the original like edge crack. So until here, we have mimicked the previous observations as we have seen from the wing of the dragonfly. So then we're gonna talk about how to connect the wavy part and the flat part together. So how to generate those dislocations in the transition area. So for that part, we're gonna to take the phase field crystal model. So when we talk about the phase field crystal model, I find it might be helpful to understand it better by comparing it with the molecular dynamic method and also the traditional phase field method. So the PFC, the phase field crystal model, is a further development of the phase field model. So phase field, as you may know, is a continuum theory, and it's based on a free energy functional to describe the system as a function of the varying order parameter. So the order parameter you can see here, it describes the greens of the phase and the greens inside of the polycrystalline system. And on the other side, molecular dynamics describe the system as a collection of discrete particles, and the atoms move according to the Newton's second law, and the driving force is just the interaction between atoms. So the timescale of molecular dynamics is severely limited due to the fast atomic vibration. And the phase field crystal operates, in fact, in between of these two regimes, but kind of similar to the phase field model. So PFC, phase field crystal, describe the system as a continuum medium and involve a free energy functional. But the free energy functional does not average over the atomic distance as we have seen from the molecular dynamics. And so this picture shows a typical density field in phase field crystal modeling and the simulation. So where non-uniform density area present a green boundary, as you can see from here. So there is a kind of transition from one green to the other. So we can identify the green boundary or twin boundary if you like to use the method to study the metal system. And the elasticity, plasticity, dislocation, green boundary, all those formations are inherently incorporated in this phase field crystal model. And as a quick summary here, so in phase field crystal model, so the fast atomic vibration is filtered out. So that means we don't have the limitation on the time scale, but we can still retain the atomic resolution, which can help us characterize the formation of the green boundary. So the PFC starts from the similar construction as the phase field crystal. So it starts with construction of the free energy functional, and we are looking for the solution which can minimize this function. And to find this minimizer, it is convenient to write the density profile in terms of the reciprocal lattice vector and the amplitude. So once we identify the wavelength and the periodicity, the pattern of the density field can be defined. So for 2D pattern, it is usually involved like 3 phases. So for example, this homogeneous phase, strip phase, and a triangle, or you can as an inverse pattern is the hexagonal phase. So if we bring this minimizer back to the energy functional and solve the minimization problem, so the amplitude of the amplitude and the wavelength can be obtained here. So the wavelength is actually related to the lattice constant of a crystal. So for example, for graphene, so the bond length is about 1.4 nanometer, and then we can kind of determine the crystal structure based on the density distribution. So until here, so now you can still see like two free variables to be determined. One is the average density, the reduced average density, the phi bar, as you can see as the horizontal axis in this picture. And also the second one is the reduced temperature, which is the vertical axis, the epsilon. And this phase diagram shows the relation of these two parameters and the pattern formation, so which can guide us on choosing proper parameters for the desired pattern. So for our hexagonal graphene structure, so we would like to take the parameter set as highlighted here, so the 0.18 and the 0.1 for the reduced density, average density, and the reduced temperature. So the density in phase field crystal, in fact, is a conservative field, and therefore we should have a balance of mass conservation, a Gaussian equation derived out based on the different construction of the functional. And for our case, so in fact, this Gaussian equation is more like a Cannickiller type 6-order partial differential equation. And of course, the finite element method can be a very useful tool to be adopted here to solve the Gaussian equation numerically. But before we apply the finite element method, we still would like to do some kind of order. We still want to reduce the order from the 6th order to 2nd order. So by introducing the new variables, we can do that. As you can see from here, the equation split for the finite element for the Gaussian equation, so that we can apply the finite element technique for the numerical discretization. And also we want to apply the periodic boundary, and so eventually the surface and the edge terms can vanish because of the periodic boundary, so that it can facilitate our numerical investigation. And the time discretization and is listed here at the bottom, and also the space discretization is just about the what kind of elements we want to choose in our finite element simulation. So here we want to use the triangle element to solve the problem. And all numerical implementation, in fact, is performed on the platform of Phoenix. And the Phoenix, I would say, is a very user-friendly platform. So it provides the a Python interface for user to implement the customized or the newly derived equations to be solved with a finite element method. And in order to demonstrate the applicability of the phase field model to the 2D system, so we first would like to use this method to study the green boundary, to construct the green boundary. So in fact, there are many ways to construct the green boundary in the 2D material for the very some typical angles or misorientation angles. So for example, for this kind of symmetric green boundary or asymmetric green boundary. So the theory here we want to adopt is called the coincidence set lattice theory. We call it CSL. And it's kind of similar idea as the standard chirality indices of the carbon nanotube construction. So here we basically just choose a pair of integers according to the matching a vector of the adjacent greens. So if the two greens have identical a matching vector, basically we can construct the symmetry a symmetric green boundary. But if we choose different matching vector, we are able to construct the asymmetric green boundary. So we're going to compare the phase field, the green boundary constructed by the phase field crystal model against the structure constructed by the CSL theory. So in order to make the comparison very rigorous, we first consider this kind of like anti-symmetric like a grain boundary to ensure the periodic boundary condition can be applied appropriately, and then we define the initial condition for the phase field crystal according to the atomic position constructed by CSL. So basically, we take the CSL, the green part, as the input, the initial condition for our phase field model, and then we let the system to run to achieve the equilibrium state, so that we can identify the structure for this green boundary area. So right now you can see that the top, like a red area, so those are the information from the CSL, but the bottom, the gray area, are the initial condition for our PFC model. But we can see that we reserve this green boundary area as an amorphous phase. So that means at the initial state, we don't know what is the green boundary structure, and we want to let the phase field crystal tell us what is the green boundary formation with the lowest like energy, potential energy. And here shows the this two pictures shows the results, the comparison between the CSL and also the PFC. So as the system achieved a steady state, so we can see that the both PFC and the CSL can give us pretty the same like dislocation green boundary structure for the low misorientation angle. However, when the misorientation angle go beyond 40 degrees, we see some kind of different structure. So the reason, so in fact, in CSL, so because of the mathematical like a matching vector, so most all the like a dislocation pair are more can be constructed as a cluster much more easier than the like a discrete, as you can see from the PFC. So we can now tell which one is more energy variable. Therefore, we compute the potential energy for the two like different dislocation pattern, the clustered dislocation and the dispersed like dislocation. So we compute the formation energy for both like a 2D as a 2D problem and a 3D problem. So from here we can see the triangle represent the energy of the green boundary constructed by the phase field crystal model. Therefore, we can claim the structure, the green boundary structure constructed by PFC can give us more like an energy favorable formation, so which is more realistic than the CSL formation. So now I think we, so from there, we have built up some confidence to move forward to study the topologically designed graphene. So the first example is the nanobubbled graphene. And so here is the step-by-step procedure to construct the nanobubble graphene by PFC. So we first set up the initial boundary condition as just what we did for the previous case, and then we let the phase field crystal model to run and tell us the density distribution, and then from the density distribution we can extract the high density area to serve as the atom location. So from there we can see that we see some kind of dislocation formation in the transition area between the bottom like a flat surface and the top flat surface, and then we can somehow design the pattern of the nanobubble graphene. So here you can see the tight packing like graphene as a hexagonal like arrangement. So in fact, the nanobubble graphene is not just by our imagination. So it has been fabricated in lab. So in fact, in 2010, so people has already found that the weakly coupled graphene monolayer is periodically rippled due to the compressive strain from the latest mismatch between the ruthenium like a substrate and the CVD grown graphene, so which gives rise to the periodic moral humps. And by some kind of modern technique, we are able to connect those kind of small humps into a larger bubble. And so in fact, so although we do not, so I mean, there is no report at the current moment to show the crystal structure along the transition area, but it is fair to predict that the defects could be introduced during this such complex growth process. And also, according to our previous result, so we can expect some defect scars in the transition area to stabilize this kind of nano bubbled graphene together with the flat sheet around the neighbor. And so according to the TM image, so in fact, the bubble height can usually range from 0.5 nanometer to 1 nanometer, and the diameter can range from 1 nanometer to 8 nanometer. So based on those information, we kind of can start our topological design for our nanobubbled graphene. And the design parameter can be the length of the unit cell, and also the diameter of the bubble, and also the height of the bubble, and even the shape of the bubble. So here we choose 3 representative samples with bubble diameter equals from 1 nanometer, 3 nanometer, and 5 nanometer. And for each set, we choose 2 different height, 1 nanometer and 2 nanometer here. So we can also design like a different shape as the circular shape, square shape, and the elliptical shape. I can show you some results in the next slide. So first, we do the stress strain like measurement. So we perform the uniaxial tension test for 3 kinds of nanobubbled graphene, assembled with like different size and the shape of bubbles in different pattern. And as you can see from here, so the blue line is for the nanobubble graphene with a relatively lower density, but the black line is for the graphene with higher density. So the red line, in fact, is for the nano bubble graphene with elliptical shape, as you can see from here. So assembled inversely, like across with each other. So the red line shows some kind of abnormal double peak stress strain curve. That is because of the trap of the crack tip trapping by the vertical and the horizontal elliptical bubble. So after the first stage, like a damage propagation, the trapping mechanism plays a role and the material can afford further loading. That's why you can see the second peak over there. So a general conclusion, so in fact, we study a lot of different pattern and the different density of nanobubbles. The general conclusion we can draw here is that the Young's modular can monotonically depending on the relative density of bubble. So meaning that more bubbles make the material more softer. So for the study of fracture behavior, again, we still perform the simulation for a sample with edge crack, and compare with so on the left you see the crack propagation for the pristine graphene, and on the right you see the fracture, the damage evolution for the nanobubbled graphene. And we can also compute the fracture toughness. And from this table, you can see in fact the medium bubble can give us the highest like fracture toughness, which can be 4 times of the pristine case. And on the right, this picture shows the 3 snapshots. So at the initial stage, again, we see the crack tip trapping, and we further increase the loading, and we see the doctor crack generation initiation, and then when approaching to the final stage, we see the obvious like a crack path deflection and the appearance of the nano cracking across the whole specimen. So again, so these are all of this mechanism can serve as the energy dissipation mechanism for the 2D material. So besides the enhancement of the implant fracture toughness, so the nanobubble graphene also show an enhancement of the out-of-plane penetration resistance. And the current experimental study has have shown the graphene damage shape under external bullet impact. So we reproduce this process. We shown quite similar phenomenon, and we try to compare this with the case of the bullet the bullet impact on a nano bubbled graphene, and we see some kind of confined a trapping area for to resist the out-of-plane impact energy. And in the bottom picture, we see that, so in fact, the horizontal axis is for the penetration time, and the vertical axis is for the kinematic energy. And the results show that the bubble graphene can absorb more than 200% energy during the penetration process. So beyond the mechanical properties, so in fact, the topological design of graphene can bring in more interesting features or properties for the thermal part and the electrical part. So for example, for the thermal part, we try to utilize this kind of wavy pattern to serve as a barrier for the heat flow. So we can somehow to manage the heat flow. And so according to this paper, so the resistance of the green boundary can achieve around this level as like a 0.05 to the maximum. So with the not wavy design, the wavy pattern, we can increase the resistance to like 2 times of the green boundary. So it can be a more effective boundary to control the heat flow. And also, we found out another interesting phenomenon, which is like the string can somehow like increase the. So with the apply the string, external string, we can increase the thermal conductivity of our sinusoidal design like a graphene. So that's still like under studying, but we have shown some preliminary result. So for example, here when we apply only 2% like a string, the black curve, that's considered as more like a standard case, so which didn't show too much enhancement. But if we increase the external string more and more, like to the 4%, 6% and percentage, and all the way to the 10% shown as the pink color, then in this way we can increase the thermal conductivity significantly. And with that, I think I would like to just close my today's talk. So as a quick conclusion, so through the topological design, we can tune the in-plane and out-of-plane mechanical property of the 2D material. And meanwhile, we can through the topological design, we can enhance the thermal property, and we can manage the thermal flow, heat conduction, the direction of the heat conduction. And more designs can be studied further. So in fact, I think the design is still a very rich area to be investigated further, like this kind of paper. Inspired by the paper like origami pattern, we can design the graphene structure with some kind of bistable like states, and similar as the bistable structure of our straw. So we can do some similar things, and even better, we can do some kind of porous design to be applied to which has some potential to be used as the electrolyte because of the high like surface and the volume ratio. And with that, I would like to thank you for your time. And here is the picture of our beautiful campus, and and also the Niagara Falls, in fact, is just our neighborhood, like 30 minutes driving distance. And if there is any possibility, any opportunity, I would like to invite you to to visit our beautiful campus. And with that, I would like to thank you, and I'm able to take your questions from here.
Thank you, Joanne. So very comprehensive and the very interesting research on the graphene and 2D materials. So any question from our audience? You can, if you have question, you can unmute yourself and then ask Dr. Ni directly. Hey Ni, do you have any question? Yeah, maybe I can start with my question. You previously when you introduced the phase field crystal model, you mentioned that you can retain the atomic information. So I'm not sure how you can retain the atomic information.
Yeah.
So there's a kind of how you can couple the phase field, the free energy function with the atomic simulation.
Yes. So that's a good question. So in fact, here, so the traditional phase field crystal, so it's based on construction of the free energy function or something like this. Here, the free functional, I think this free functional is more complex than the phase field, traditional phase field model. So here we can see a fourth order like a term in for this phi function, and in this phi function, is further developed as a function of the lattice vector and also the amplitude. So this the new form of this phi function is the key information that we want to integrate in the PFC model, because in all the solution, so those minimizers of the function, they are function of the Q and the K, the AS. So those are the information which can help us return the crystal crystal like information, like the lattice constant and also the distribution of the lattice constant. But the main idea here is to just correlate the density distribution with the crystal structure, so that our assumption is that the high density area, so are the location where the atom should appear, I mean, with higher like a chance. So this kind of minimizer can describe the crystal structure, crystal information based on this kind of proposed form as the minimizer of the function.
Okay.
Function, yeah.
Okay. Then later when you use the phase field, the finite element simulation for the phase field results, then you can use the results to initialize the lattice structure. I'm not sure what information you are using to initialize the green boundary location.
That is just the density. So here you see this sixth order partial differential equation, the phi function, that is the density. So it's just like the unknown variable in our traditional finite element method. So the displacement, right? The location, the position. So here we are switching the unknown variable from the position or the displacement to the density. So the density is a varying function across the whole specimen. So therefore, for our initial boundary, so the top part are from the CSL. So that's the known information. And especially for the green area, we know what is the direction of the greens. So with that, we based on those information again, so those atom location are the high density area. So we just initialize those area with phi equals to 1, but for other area we set up phi equals to 0. And for the green boundary area, so we don't know what is that. So we just use the 0.5 to represent amorphous like state, amorphous phase. But when the system achieves the equilibrium state, so it can give us some kind of density distribution. So from there, we can extract the atom position.
Okay.
Mm-hmm. Yeah.
So, okay.
Yeah, and besides the initial boundary, we also have the periodic boundary. So that can make the mathematical equations in a closed form, so we can solve for the solution.
Okay, so you still need to use the when you use the phase field information to generate the lattice structure, you still need run a simulation to reenact the system to some equilibrium state, right?
Right, this is the PFC simulation. So you can see at the very beginning, so we have this initial condition. So you see the alternative of the red color and the blue color. So basically blue is 0 and red color is 1. And then in the middle, the transition area, because the transition area is usually the tough part, the tricky part. We want to use phase field to tell us what is the density distribution. So when we run this PFC simulation, basically we are searching for the minimum like energy state with the density identified near the like transition area. So we can tell where are the atom position. And from this, so for example, for this particular area, so we see some kind of so I'm not sure if you can see my cursor, but we sometimes see this kind of pentagon shape, but sometimes we see this kind of hexagon. But we also notice that near the pentagon, there must be a heptagon to compensate the topological geometry, the topological feature of the mesh. So that's why we always see the pentagon and the heptagon pair close to each other to form the dislocation dipole. So it can serve as the basic element to construct the green boundary. So
okay.
Yeah.
Yes. So can go to the slides 23.
23, yes.
So for the second simulation, you use the graphene with large bubbles. So I see all the 4 boundaries shrink to the middle. So I'm wondering what's the boundary condition you are using for this simulation?
Oh, for this one, so in fact, it's a visualization problem. So this is a molecular dynamics simulation, and we are applying a tension force on the top and the bottom edges. So we are pulling the sample. So I'm not sure. So you see this kind of black color, that is the simulation box. And when we pull it, we just cut off the picture into that particular area. So
okay. So
yeah,
this is not the entire system. You are zooming in this sample.
Right. Just focus on the corrective area.
Okay. Then can you go to the next slides?
Yeah.
So for the when you do the penetration experiment, I noticed there's I suppose you are using periodic boundary condition or other boundary.
No, so here the boundary is called the absorption boundary. So we do not allow the energy. So here it's a wave propagation, right? When the energy approach to the boundary, so we use the absorption boundary condition to absorb all the energy. So those waves will not go back to the middle of the sample.
Yeah, this is my question. I suppose the boundary should absorb the wave, but if you play the movie, this one, you will see the wave will reflect the boundary. You see that?
Yeah, so I think I believe we use the absorb boundary. I think that's So we have like multiple like peaks to go together, but the peak may also interact. So I have to confirm this one, but I think for all this kind of topological design, like sample, we use the absorbing boundary, but for this one, so I have to confirm with this.
Yeah, because I can observe the wave reflect
Yeah,
from the boundary. So
right.
this is one interesting I see. I suppose you should use
Yeah,
absorbing
observing.
condition
Yeah,
for
we
this
should use.
penetration test.
Yeah, this one I cannot recall exactly. Oh, but maybe this one we don't use because so considering to compare with the experiment, like in experiment, they also fix the boundary of the sample. That means the boundary is kind of a fixed boundary that can reflect that can make the wave to be reflected from the boundary. I think maybe because of that consideration, we use the fixed boundary in this pristine case. Instead of the absorbing boundary. So
this simulation is done by NAMS or by any
by
other?
LAMS, just by LAMS. Yeah,
So
all molecular simulations are done by LAMS.
So does NAMS have the absorbing boundary condition?
I don't think so. I think we do a little bit further development to integrate the absorbing boundary.
Okay.
Yeah. So, but there is a very nice paper talking about the absorbing boundary. If you are interested in, I can send.
Yeah. I know this is the challenging problem. How to, because if you're talking about the absorbing boundary, you need to think about the history of boundary condition.
Yes.
So that you can observe different wavelengths, this kind of thing. It's not an easy boundary condition.
Yeah, but I think the paper, I think there is a paper published on PRB. So that paper gave a very neat mathematical expression to handle the absorbing boundary. So I can definitely find that for you. So
okay, great.
Yeah.
Thank you, Joanne. So any other question from our audience?
So in fact, this topic, I haven't touched this topic for a while, and I always thinking how I can I can get back, and hopefully this can be a good starting point.
Yeah. The 2D material is very interesting.
And especially the topological design, like how to utilize the soft part and integrate the soft part together with the hard part to make the structure more tough, and maybe also some other interesting physical properties. So
yeah, Henny, you have a question?
Yeah, hi, Joanne. Sorry for joining late.
No,
it's an interesting simulation result. So I just have a general question because I do not know the specific solid material problem very well. So in LAMPS, could we do some flow structure interactions? For example, for this crack propagation, could we also simulate the flow inside kind of the force drive the crack come from the pressure of the flow instead of you directly apply them?
Yes.
Is that possible to do it using lamps?
Yes. Depends on your system. Say if you just want to use water, then there are some like a standard potential you can use. So basically, I mean, we know that molecular dynamics is just a particle method. Then when you know your solid material and you know your fluid system, then you can use the corresponding like a potential to describe the system, and then the interaction is kind of nature. So if you like to study the reaction, there are some kind of potential regarding the reaction between the two chemical components, or if you just like to study the pressure, then the stress can take the pressure naturally to the system, and then you can study the solid fluid interaction directly.
Okay, so can we right now easily do it using lamps, or we have to implement something?
I don't think you need to implement anything. So there are it's just a standard like operation in lamps, but you may have to be very specified regarding the material, like the solid material, because you're gonna to choose the appropriate potential to describe your solid and your fluid. So in water, so right now we are use the tip potential for water, and there are also some other potential for water. And for hydrocarbon, there are also some standard like potential for users to use. And for the material, so for example, for this graphene, we use the Aribo, and we can also use the Tursoft. So there are a lot of different potential. You just need to choose appropriately according to your problem. So
okay, and also could we scale up the simulation for the solid here? For example, because I see this the simulation scale is like 50 Armstrong, right? If I want to scale it to 50 micro, is that possible to do that for the solid one?
I mean, for micron, it might be challenging, but for this one, I believe it's about like 200 by 400 nanometer. So 2D material is okay. It is possible to scale from nanometer to micrometer, but consider the bulk material, like 3D material, then you're gonna to have a lot of like items to describe your micrometer system. So the computational effort is significant. But but 2D material, it might be possible because we just have a layer. So it's possible.
Is there a good a continual based method can do the clock propagation? I know finite element is they do clock propagation, but it's a fake model. Wondering if there's any good option in the based
I think there are multiple options. So first of all, if we consider continuum model, so the meshless method, so meshless method can be an option, and also the DEM, discrete element method, can also handle the crack propagation in the porous medium. And also the phase field model. In fact, there are a lot of people are trying to use the phase field model. Let's go back to here. Maybe, I don't have the information here, but the phase field model is also widely used to study the fracture propagation, especially the complex pattern, like the crack, like divergence, and also just the complex like fracture pattern can be handled pretty well using the phase field model as well.
Have you tried the phase field model before, or you still stick to the molecular level?
I mean, so for this particular project, we didn't use phase field model, but I know there are some package and the open source code that we can are ready for user to use directly. So there are some kind of demo code and examples that we can follow pretty well.
Okay, good. Okay, thank you for all this information.
Yeah, thank you. So in fact, the complex fracture pattern, so something like this, like the blunting, the Dr. Crack initiation. So this part considered as the complex fracture pattern is very challenged to be handled by the continuum model, such as the finite element method. But there are also some options available, depends on the nature of the problem. So we can pick like accordingly.
Okay.
Yeah.
Okay, thanks, Jiayan. So if we do not have other questions, we will end here today.
Yeah, thank you, Jen.